Hello, my people. I hope we're doing well. This is the video where we're going to be going over the answers to quiz number 3. I've already posted the one for quiz number 1 a couple of weeks ago, and also the one for quiz number 2. Before we move on, before we move to the first one, I wanted to draw everyone's attention to that right there. When you are finished, I need you to scan all pages into a single PDF. Do not use photos, which is code for do not use JPEGs. Use a scanner or a scanning app to do so. Be sure that your scanner is set to black and white and not cut. Oh my gosh, would you? That's like half of the things that I discussed in the new scanning procedure. It's almost like I wanted you to read the instructions carefully before you began. Okay. Now, you know what to do with this one. And for the most part, people did pretty well on this one. I had a few problems with picking an appropriate scale. Now, I said in the video, and I think I said in class as well, my policy my explicit policy when I was teaching this, in a 4-credit class and stuff like that was, I want to see, you need to scale it so that I can see at least 2 periods of the graph. But because I want to see at least 2 periods doesn't make 12 periods better, okay? 12 periods, or however many, is too many because they're too smushed together for me to actually see whether you have arrived at an accurate curve, okay? The difference between the correct point and an incorrect point are too close together and too hard to make out, okay? But we do need to remember that when we're dealing with tangent and there's no period change, which in this case there's not, an appropriate scale is basically every 4 boxes. And the reason, pi being every 4 boxes, and the reason for that is the convenient point that we want to grab onto when we are doing our graphs of tangent occur at pi over 4 and negative pi over 4. And because of that, we want to sort of abandon the pi being every 3 and each box being pi over 3 because we don't want to ish those really significant points. We want the scale to accommodate those significant points, okay? Now, in terms of tangent, I know that my parent looks something like this. And yes, I did expect you to draw the parent, okay? And it looks something like that, okay? And you'll have on the parent, you'll have an asymptote here and an asymptote here. And remember that it has a period of pi. So all of these points, and I'm gonna skip drawing the asymptotes for the parent because that's just gonna clutter the graph a little too much. It looks something like this. Okay. Now, I need to now identify the transformations, which I'll do over here. I need to move to the left, pi over 4. Okay, I need to vertically shrink by 1/2, and I need to move it down 1/2. Some of y'all lost points because, like I just said, you scaled it inappropriately. Some of you lost points because you scaled it in a way that I couldn't tell whether you understood the scale or not. Some of you lost points, there were a myriad of, some of you lost points just because the graphs were sloppy, okay? The whole point of graphing, I don't expect them to look like they just came off of a graphing software program and were printed out. But there's a certain neatness and tidiness that I do expect, okay? So let's take this middle period right here and we'll transform it and use it as representative of the rest of those points. And of course, when we do that, we'll be focusing on this convenient point, that convenient point, and that convenient point, as well as the asymptotes, okay? So let's take the intercept. Let's move it over pi over 2. It's going to stretch by 1/2. Well, 0 doesn't stretch. And then I'm going to move down 1/2. Okay, and that happens every pi. So I can go ahead and put those in right there. Let's take this point right here. Let's move it over pi over 2, pi over 4. Let's chop it in half, and then we'll move it down 1/2. And you have this point. Okay, well, that also happens every period. Okay, let's take this point at negative pi over 4, negative 1. We'll move it over pi over 4. We'll chop it in half, and then we'll move it down 1/2. And we get this point right here, which of course, because of the periodic nature of the function, occurs every period before and after that. Okay. Now, if there's been no period change and everything has shifted to the left pi over 4, that means that so have the asymptotes. So the asymptote that was here is now here. The asymptote that was here is now here. The asymptote that was here is now here. And just like the other points, the asymptotes have something to do with the period as well. So we'll just draw them every pi. And then we just need to sort of connect the dots in an accurate, smooth curve. And it should look flatter than the parent, okay? Because it's been shrunk vertically, right? And so, like, a lot of it looks just as steep, but especially this middle portion right here, right? It's been compressed, and so we see the fact that this is considerably steeper than this is right here. Now, when we're looking for the stuff down here in terms of algebraic, most of y'all did pretty well on this. It's not second nature to a lot of you yet, and that's understandable. We just started doing it, right? But let's go ahead and look for the x-intercepts of this transformed function, which is a nice way of saying, Mr. Function, let me ask you a question real quick. When, sir, are you 0? Well, let's go ahead and use our algebra skills in terms of determining the solution to an equation, solving an equation. We need to figure out what's being done to the variable and undo it in the opposite order, right? Okay, well, what's being done to x? Plus pi over 4 tangent times 1/2 minus 1/2. And so I need to undo it in the opposite order. I need to undo the minus 1/2. I need to undo the times. Now I need to undo the tangent. And this is a question when you're going from here to this next step. If you want to, you're asking the question, when is tangent equal to 1? Well, tangent is equal to 1 when the angle measurement is pi over 4, or every period after that. When the angle measurement, no matter what form that expression takes, the answer is when the angle measurement is equal to this. And then you solve it further from here. And I do want you, if it winds up being 0, I do want you to include the 0 plus pi n, not just pi n, okay? Show me the 0, give me that, okay? Let's look at the next one. Negative 2 secant x over 2 plus 2. Alrighty. Now, that means that I'm going to have a period change, right? I'm going to have a horizontal stretch of 2, which means my period is now equal to not 2 pi, but 4 pi. I know that I'm going to have an x-axis reflection and a vertical stretch of 2, and then I'm going to ask you to move it up 2. Now, most of you did not choose a scale that would accommodate seeing 2 full periods. And that's fine. You know, I didn't make that requirement very, very strict on you guys. I'm more interested in whether you're understanding the general contours of transformations and how they apply to trig functions. So we will, like most of y'all did, we will go ahead and use the usual scale. And what we're gonna find is that we'll see 1.5 periods of this, which is enough. Some of y'all, however, did not do a good job of scaling it vertically. Okay? When you choose an appropriate scale, that scale needs to ensure that the significant points of the curve are on the Cartesian plane and not somewhere off the Cartesian plane, right? So you don't want to use the scale that we had where it's, you know, -2.5 to 2.5, where every 4 boxes is 1 unit. But if I know that I'm moving up 2 and I'm stretching by 2, I know that my minimums up here for secant are going to go from 1 to 2 when they stretch, and then they're going to go up to 4. I was okay if you went -5 to 5. It would have been better to scale it even more aggressively than that, because there are the next points up, the ones that are originally at y is equal to 2 are going to wind up being at 6. But let's go ahead and and I didn't take points off if you got it that way. However, if not even the minimums were on the Cartesian plane, I did count off. Okay, let's draw the parent. 1, 2, right? And then 1, 2. And the asymptotes kind of run right here, right in the middle here. And I'm not going to draw them because that's just going to be distracting for us, but we do need to know that they're there, okay? Pi and 3 pi, and then 2 pi. And what I'm talking about is the points that are originally at 2. What I'm saying is that once we do the transformations, these that are originally at 2 are going to be up at 6, which is going to be off the Cartesian plane. But we'll just kind of deal with that. Okay. And you need to be precise enough with this graph such that I can tell from the parent to the transform graph, I want to be able to see the steepness increase. Also, if you drew these so that some of the lines crossed the asymptotes, which they can't, right? If you were sloppy and they overlap the asymptotes, yes, I count it off. Okay, that's inappropriate. That just doesn't happen. Part of what we're doing here, I mean, precision is not the whole of what we're doing here, but it is part of it. Okay, so let's go ahead and go point by point. I need to horizontally stretch this. Well, you can't stretch 0, right? Then we're going to x-axis reflect it, stretch it by 2, and move it up 2. Okay. Let's take this point. We're going to horizontally stretch it by 2. Then we're going to x-axis reflect it. Then we're going to stretch it by 2. And then we're going to move it up 2. It goes right here. And because there's sort of symmetry between the asymptotes, you know this point implies that point as well. You also know that you have a period of 4 pi, right? Well, that means that this happens every 4 pi, and of course that's off the Cartesian plane. Let's go ahead and take this point right here. I'm going to horizontally stretch it. It is now 3 units away from 0. I'm going to make it 6 units away. I'm going to x-axis reflect it, stretch it by 2, and then move it up 2. And I get this point. Well, this point I can extrapolate in terms of the period because -2 pi is 4 pi away from +2 pi. Let's go ahead and take this point right here. It is 2 units away from 0. Let's stretch it. Okay, let's reflect it. Let's stretch it by 2, goes up to 4, and then we're going to move it up 2. And so actually, see, that point gets put up there, and by symmetry, this point gets put up there. Now, if you did this, I didn't count off, even though those are pretty significant points and they're off the Cartesian plane. But we do, it's pretty important that those points be on there. Now, I know that the original asymptote is here, right, at pi over 2. It stretches out to pi, and so we get an asymptote here. We get an asymptote at negative pi, because remember, on a secant and cosecant graph, when the period is however long the period is, there are 2 asymptotes per period, right? Because there needs to be an up and a down. Okay. Okay. And some of y'all gave me a graph like that, and as long as it was pretty and you didn't like come across the asymptote or something ridiculous like that, I give you credit, okay? But it needs to look something like that, and it needs to be tidy, and it needs to be accurate, and the parent needs to be on there, and all sorts of fun stuff like that. Now, some of y'all misinterpreted this because, but that was evidence to me that you either didn't watch all of the videos or you didn't watch them carefully, because I discussed this. When I'm looking for minimums, I'm not looking for what are called absolute minimums, because there isn't an absolute minimum, because this goes down to negative infinity. When I'm looking for the minimums, I'm looking for relative minimums, local. Like with respect to all of the points in its immediate vicinity, that is the lowest point. I don't care that it's higher than that is. With respect to the points in its immediate vicinity, that is a minimum. With respect to all of the points in its immediate vicinity, that is a maximum. I don't care that that point is higher, and I don't care that this portion of the graph goes up to positive infinity, and there is no absolute maximum. I'm talking locally, okay? So basically, I wanted you to algebraically figure out these points, okay? Which means you're asking the function, Mr. Function, when are you 4? Okay, well, let's go ahead and we'll start undoing the order of operations. That becomes 2, and that's asking the secant function, when is it negative 1? Well, where is secant negative 1? Well, this is another benefit of having drawn the parent function, right? Where is secant negative 1? Well, that's the same place where cosine, okay, where cosine is negative 1. And cosine is negative 1 here, 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 right? And that's basically at pi and every coterminal. So that's basically x over 2 is equal to pi plus 2 pi n, and x is equal to 2 pi plus 4 pi n. Now, does that accord with the graph? Because some of y'all did beautiful work down here and didn't use it to go back up and check whether this matched this. And they should match, right? If your minimums by algebraic method tell you that 2 pi plus 4 pi n are your minimums, then 2 pi and every 4 pi before and after should be your minimums on your graph. Okay, well, let's look at solutions. And by solutions, I mean, of course, x-intercepts. Where does this graph intersect the x-axis? So you're simply asking the function, Mr. Function, where are you 0? Well, let's go ahead and undo the things that are being done to the variable. And when we get down to here, instead of being asked where is secant negative 1, we're asking where is secant positive 1. Well, again, if you want to make recourse back to cosine, since it is the reciprocal of secant, or you can just look at where secant is positive 1 on the graph, okay? It happens at 0 plus 2 pi n. which means that you should get 0 plus 4 pi n. Again, please do remember to include the 0 plus, and those should be our x-intercepts. Now, they happen to be x-intercepts of tangent c, but it hits the x-axis nonetheless. Okay. All right, let's go ahead and move on. I asked you to define inverse. I defined inverse for you. Okay, and the word that I was looking for, the definition that I give you is that which undoes, right? And the undoes is what I was really looking for. It's not so much that they're opposites, because if I say, hey, you know, what's the opposite of 1? But it's not so much that they're opposites, it's because they have, especially with respect to a particular operation, they have sort of opposite charges, I guess, for lack of a better word. One undoes the other. That's why when you're solving an equation, you have x plus 2 is equal to 7. You subtract 2 from both sides because negative 2 is the additive inverse to positive 2. Okay. And so I really want to focus on the idea of it undoing, okay? And I was very explicit about that in class. Again, the things that I say are not optional for you to remember, nor are they incidental for the assessments and your understanding of what it means to think mathematically, okay? I'm trying to train you how to think mathematically in the midst of teaching you the content and curricular procedures for calculus, okay? Now, the next 3 sections of questions were basically, you know, do you understand what's going on in the different ways that inverse trig is applied analytically? Now, remember that when we are dealing with trigonometric functions, we are dealing with things that have a single output. Okay? So if you were thinking about this, and if you wanted to do it by the unit circle, you could go, okay, well, where is sine equal to 1/2? Well, here and here. But because it's a function, and you remember that this is not included in the range, it winds up only being pi over 6. It's a function, okay? It has a single output. Same thing with arc cosine of negative root 2 over 2, okay? If you wanted to do it by this, you would say, okay, well, negative 0.7 is out here, so that actually winds up being here or here, but remember, inverse cosine doesn't allow for these values. It is only this value, and therefore it is 3 pi over 4. Okay, and so there were a couple people who included the, you know, plus pi n, plus 2 pi n, and stuff like that on these, but you can't, okay? You cannot. This is, or they included the second value, right? They included the 5 pi over 6, and they included the 5 pi over 4. It is a function. I was very specific about function. These are the type of things we did on day 1 of inverse trig. And I made the distinction, I made the parallel basically between it's different when you're given inverse trig than when you yourself take inverse trig. The same way that when you're given root 4, you're asked for a single output, positive 2. When you are the one to square root 4 in the midst of solving an equation, it is then that you need both values, okay? Well, let's go ahead and move on. These are the ones that are not so restricted because we are dealing with it as an operation in the midst of solving trigonometric equations. The problem is that some of you didn't see this or just paid it no heed. Now remember, when we're dealing with sine, we're dealing with y values, and so it's this one and this one, okay? Now, some of you might want to call that negative pi over 6, and if you were dealing with an interval other than this, you'd be right. But because I'm only dealing with positive values in that first revolution, I have this and I have this, okay? which is basically x is equal to 7 pi over 6 and 11 pi over 6. Those were your answers. Now, when we got down to this next one, it was a little bit trickier because that's not a value that's going to give us a unit circle, 5 pi over 4 or anything like that, right? That is going to give us something, that is going to give us an angle measurement that needs to be discerned by means of calculator work. Now, some of you gave me degrees. No, okay? Unless we are dealing with something that something where you are specifically asked for degrees, or it's a word problem and we're talking about angle of depression or angle of elevation, or we're talking about a boat on the water and it's bearing north 35 degrees east or something like that. Except for those very few circumstances, unless it is stated otherwise or it is very clear from the context, you give me radians, which means that you need to program your calculator to be in radians, and we need to take the inverse tangent of negative root 2. Now, there's a problem with this, because when you do that in your calculator is using arctan as a function. That's why it only gives you one. That's why it only gives you one value, okay? But, so basically you have x is equal to negative 0.955. But that's negative, and my interval here implies that it's two positive values, okay? So what we have here is, if you were to actually draw it, and you can, you need to remember that this is basically -1, right? -1, and one radian is approximately pi over 3, right? Because pi is 3.14. And so you can ish it, you can say, it's somewhere right around there. And of course, since tangent has a period of pi, it's up here as well, right? But here's the problem. This right here is your negative 0.955. What I need is this value and this value. So what I needed to do is I needed x is equal to negative 0.955 plus pi, and x is equal to negative 0.955 plus 2 pi to give me both of those based upon the period, okay? Now, what you do here is you simply add pi and then add pi again, okay? And those are your two answers. Don't leave it like this. If you've already done an approximation, by the way, when you do it in your calculator, you use the actual value, okay? You use the non-approximated value to then go ahead and add pi to those two. And you get, and these should be squiggly as well, right? All these should be squiggly since we're dealing with approximations. 2.186, and this is approximately 5.328. Always to 3 decimal points. Always to how many decimal points? 3 decimal points. We've been over this before. Okay. Now the last two are of the same variety, but we're given a negative infinity to infinity. So this, of the 3 varieties of problems that we are dealing with after our graphing, these are the ones where we have the plus pi in and plus 2 pi in, okay? Okay, so cosine x is equal to 1. Well, you're asking yourself, where is cosine equal to 1? Well, cosine is equal to 1 at 0, where the angle measurement is 0, and every 2 pi in after that. Okay, secant is equal to negative root 2. Well, let's go ahead and change that into cosine x is equal to negative 1 over root 2. And then, of course, that winds up being that when you rationalize the denominator. Well, where is cosine x equal to negative root 2 over 2? Well, we've already answered that question because, remarkably, it was back here, right? But now, instead of being relegated to this one measurement, we have both of them and all of their coterminals, okay? And so, you know, if you go over here and you get these, you get, you know, 3 pi over 4 and 5 pi over 4. And so you get x is equal to 3 pi over 4 and all of its coterminals. And x is equal to 5 pi over 4 and all of its coterminals. So when you're dealing with the analytic work that is involved in inverse trig, you need to be very careful about being given inverse trig and you being the one who's taking inverse trig. And if you're dealing with a trigonometric equation and you're the one taking it, you need to be very careful about being mindful of the interval that is given, okay? The interval here is negative infinity to infinity. So it's the plus 2 pi n, plus 2 pi n, plus 2 pi n. Here, it was just 0 to 2 pi, and therefore I needed to be very careful about making sure. Now here I used the period in order to adjust what my calculator gave me, but I did only give those two values that were between 0 and 2 pi. Okay. If you guys have any further questions on any of this, please do shoot me an email or a message in Teams. Bye.